Good evening, everyone. I'm Harindu Abhigunaratne, one of the board directors of SLASCOM. First of all, let me welcome you all to the final day of the Digital IT BPM Week 2020, the first of its kind to be launched in Sri Lanka by SLASCOM in collaboration with the Export Development Board, ICTA, and FITIS, with the support of a number of industry partners. So this initiative is a brainchild of the Regional Development Forum of SLASCOM, through which we hope to engage undergraduates across Sri Lanka. So in the past few years, we have conducted similar IT BPM weeks focusing on identified regional universities. However, this is the first digital IT BPM week open to students from all regions. I know this is the last day of the whole IT BPM week, but stay tuned because from next week onwards, we will be continuing with our usual technical sessions on every Thursday, and we will keep you posted on our social media platforms. So without any further ado, let me welcome the first speaker for today, Sarala Kumarage of Simcentric Technologies, who will take you through an introduction to machine learning. Over to you, Sarala.
Thanks for the introduction, Harindu. Good evening all. Welcome to another session in IT BPM 2020. So you are joining for the introduction to machine learning session. My name is Sarala. Today I'll be talking about an interesting topic which is on its hype nowadays. So that's machine learning. Right. So before we start the presentation, I would like to go through of my profile bit, little bit about myself. I'm a machine learning engineer at Simcentric Technologies, and I have served as a technical program committee member in artificial intelligence conferences, and also I was a former data science and AI engineer, software engineer, and assistant lecturer. And I'm also working as a visiting lecturer in artificial intelligence. More specifically, I'm a researcher in currency trading platforms and expert advisors. So, a little bit about the company I work for. So we are a simulation technology company, and we have a global customer base, and we develop, maintain, and sell range of simulation products. And we have actually intellectual property focused development here in our company, and also all the research, development, and maintenance is done at our Colombo office, and we are a Bureau Veritas certified company. So this is today's outline. So today we'll be discussing about machine learning concepts, and more specifically, we'll be going to the machine learning practical sessions in Google Collaboratory. And under the machine learning concepts, we will be discussing about the human intelligence and also the artificial intelligence, machine learning, and deep learning, and how it has been evolved. And also we will be discussing about the machine learning pipeline, and there we will be discussing about the artificial neural network model design, and also we will be discussing about how the neural network comes up with the prediction with forward propagation algorithm, and we will be discussing about the model compilation and what kind of parameters we need to set up. And also we will be talking about the model training, testing, and how we can use the trained model to the live data prediction. And we will be discussing a little bit about the fault tolerance in the training phase. And also more specifically, we will be giving you some other machine learning techniques, kind of an overview in general, And in the practical sessions, we will be covering three main practicals. One is to like implement a neural network to identify or classify the images of clothing. It would be a multi-class classification problem, then binary class classification problem, and the regression problem will be covered in the practical sessions. So that's the today's outline. So to start off the things with, I would like to give you an introduction to AI and its kind of evolution, how it has been evolved throughout the years, right? So AI is a wide-ranging branch of computer science, and actually it's concerned with building smart machines, right? And it's capable of performing the task that typically require kind of human intelligence, right? So at the same time, it's a interdisciplinary science with multiple approaches, but as we can see, advancements of machine learning and deep learning are actually kind of creating a paradigm shift, right, in virtually every sector of the tech industry now, right? So as you can see in this slide, artificial intelligence is used to like make machines like learn and think like humans, right? So you can see this machine learning as a subset of artificial intelligence, and machine learning is like basically focused on like we need not to explicitly program the machines anymore, but we need them to learn by themselves and infer the information, right? So deep learning is again a subset of machine learning. So under machine learning, under deep learning, so we have a special structure called neural network, right? You might have heard about this term, and you might have come up with some experiences as well, this neural network structure. So in this deep learning concept, what they do is it learns from a large amount of data, and it infers or predicts something, right? So as you can see the evolution of artificial intelligence here. So in around 1950s, artificial intelligence has come to the picture, and machine learning came into the picture in around 1980s, and deep learning came into the picture in around 2010s, right? So far we have experienced this evolution throughout the years, and currently we are working with deep learning technologies to build some intelligent solutions, right? So before talking about the artificial intelligence, like, so I think it's important to understand the human intelligence first, and what he can do as a human, right? So as you can see in this slide, you can see as humans, we can get the information from the five senses, and we can actually infer something, right? Intelligently, right? So like this, as per to this example, or as per to this diagram, you can see humans can get information from the outer world and intelligently infer something, and so that we can come to the conclusion that like humans can think rationally, and also it can we can act rationally, right? So as you can see in this slide, so let's say if you are given an image of a cat as a human, right? So what happens is like you can actually identify it as a cat, right? So that ability is there with us as humans, right? So you got some information from your sensors and you inferred something, right? So you can actually identify this image as a cat image. So that's a human capability. And also, what would happen if you are given with an image of a digit, right? So what will happen is you can actually identify this as a digit image, right? So that's a capability that we have as humans, right? But the thing is, what we are focusing in here is like we need to incorporate these human capabilities to the machines, right? But in order to do that, machine needs lots of training like this, right? So you can see this model is being trained using a label data set, right? So in this label data set, you can see the features, right? The digits or the images, and also you can see the associated labels with it, right? And then what happens is if we train a model by using this kind of a label data set, the model tends to learn the mapping in between these features or these images and the labels, right? So then what would happen is the machine would be able to infer or come to a kind of decision about the data that we give to it based on the mapping that it has learned from this training, right? So as we discussed, as humans, we have that capability to understand or recognize this kind of images. So we are kind of training this model or machines by giving this kind of data set with like uh, original data set, and along with the features, we give them the mapping details to learn, right? So after train the model, you can actually have this train model to predict something, right? So we can use this train model to test whether actually it can predict or take an decision intelligently, like human does, right? So here you can see after training the model, if we give this kind of image with a digit to the trained model, it will be also able to identify that image as it is, right? Like if we were able to train this model in a accurate way, right? So if this can be enabled to a machine or a trained model, right, what we can achieve is like we can actually incorporate the human capabilities that the human had to these machines, right? So that's the aim of artificial intelligence, and that's the aim of incorporating the abilities or the capabilities of humans to the machines. So before we are going into other details of machine learning, I would like to give you a kind of introduction to it. So machine learning is actually a branch of AI, as we have discussed already, right? You have seen machine learning is a subset of that AI altogether, right? So this machine learning has the ability to learn without being explicitly programmed, right? So normally what we do is we program something to happen in our systems, right? But in machine learning, what we expect is we don't explicitly program anything, but we let them to learn from the data and let them to infer the correct information, right? So that's what the machine learning does. So as you can see, there are many machine learning algorithms. So we can categorize them to main subcategories. One is the supervised learning, other one is unsupervised learning, right? So under the supervised learning algorithms, we have classification and regression. Under supervised learning algorithm, we have clustering and association. So before we are going into the details of these things, let's start off the discussion with the introduction to the supervised learning. So we would like to discuss what we are going to do in supervised learning. So supervised learning is like there you have a input variable and you have output variable, right? And you use an algorithm to learn the mapping function from the input to the output, right? So in supervised learning, you have both the input and the output, right? And the mapping in between them, right? So as you can see, classification is another application of supervised learning. So in the classification problem, what we do is like when the output variable is a category such as red or blue, like it can be disease or no disease. So we can actually classify the things accordingly, right? So in regression, what we do is like we deal with some kind of output variables with some real values such as dollars, dates, and some other real numbers, right? So in unsupervised machine learning, what happens is like you only have the input data, but in supervised learning, you both had the input data and the output data, right? But in this case, you only have the input data and you don't have any corresponding output variables, right? So in supervised learning, right? And also the goal for this kind of unsupervised learning algorithm is to like model the underlying structures and or the distribution in the data in order to learn more about the data provided, right? So under the unsupervised learning algorithms, we can basically identify two other algorithms, which is clustering and association. So in clustering, we basically discover the inherent groupings in a particular data set. And also in association, what we do is like we define a rule. We define a rule where you want to discover rules that describes large proportions of your data, right? Such as if I give you a kind of example, if people buy X, they also tend to buy Y, right? That kind of scenarios we can handle with like association problems. So here we comes to the section of deep learning. As we have already discussed, deep learning is also a subset of AI and also it's a subset of machine learning, right? And here, to give you a kind of introduction to the deep learning, actually deep learning is a branch of machine learning, right? So which is completely based on the artificial neural networks, right? So as neural network is going to mimic the human brain, right? So deep learning is also a kind of mimic of human brain, right? So you can understand about that like that. So in deep learning, we actually don't need to explicitly program everything. So the concept of deep learning is like, as we all know, it's not new. It has been there for a couple of time, and it has been actually around for couple of years now. So, and the most important thing is it's on the hype nowadays, right? Why it's in the hype now? Because like in earlier we didn't actually have that much of processing power, and we actually didn't have a lot of data as well, right? So as in the last 20 years, the processing power and the other infrastructure facilities has been increased in an exponential way, right? So deep learning and machine learning came into the picture after that, right? So like if we try to relate this deep learning concept to the human brain, right? So in human brain, we have approximately 100 billion neurons altogether, right? So this picture also actually gives you kind of interactions between a lot of nodes. So this kind of similar structure is there in our brains as well, right? So, but the question is, how do we create these neurons in computer, right? So we create an artificial structure called artificial neural net, where we can have nodes or neurons, right? So we have some neurons for input value, and we have some neurons for the output value, and in between there may be a lot of neurons interconnected in the hidden layer. So as you can see in this slide, you can see the input layer, you can see some hidden layers in between, and you can see the output layer, right? And you can see the interconnections in between these nodes, and you can see inputs are coming to the coming into this network, and output is going out of this network as a prediction, right? So before we moving further, we would like to discuss about the machine learning pipeline, right? So these are the steps of machine learning pipeline. First, we have to prepare the data set actually. If we want to deal with the machine learning or deep learning project, the first and the very first, very important thing that we have to prepare is the data set, right? And also you have to take care of, like, you have to make sure that you have large amount of data with patterns. Actually, if you don't have a data set with patterns, you can't even think about a machine learning solution, right? It has to be there, the pattern should be there in order to train a model and let them behave in an intelligent way, right? And also we have to perform some data pre-processing on the data set and do some fit selection, then design the artificial intelligence neural network, then compile the model, then train the model. Then actually after training the model, you can evaluate the model that you have trained, and also you can test the model, right? And also after testing and evaluating, you can actually use the live data on the model to check the prediction, right? So we will be discussing how each and every this step is working in the practical scenarios, right? In the upcoming slides, we will be discussing each and every step in this machine learning pipeline. So to start with the machine learning pipeline, we will be discussing about a very simple design of artificial neural network, right? So the network that I discussed here has 3 layers, and it has input layer, it has a hidden layer, it has an output layer. And each of these layers have 4 nodes each, right? Like this. Input layer has 4 nodes. Hidden layer has 4 nodes. And also the output layer has 4 nodes. And as you can see, there are 4 inputs to the input layer. And another important thing is all of these nodes are interconnected with each other. So we call that kind of structure or that kind of layer as a dense layer, right? If the nodes are interconnected with each other, we call that layer as a dense layer. And the purpose of implementing this kind of hidden layer is to actually capture the interactions, right, between the data. So like this, every node get connected with each other. So we get the inputs to the input layer, and as you can see from the output layer, we get the predicted outputs. So this kind of design should be there when we are developing a machine learning pipeline, right? Machine learning product or intelligent system. So that's the first step that you have to go through. And here, apart from these details, you can define the activation functions and yes, some other configurations as well in this design step, right? So next, what we have to think about is how that kind of intelligent neural network comes up with the prediction and what happens inside, what kind of algorithms are running inside, right? So I'm going to give you a kind of introduction in simple terms, what happens or what an artificial intelligence system do inside when they come up with the prediction. Okay? So as you can see a directed graph with nodes and edges, right? So I have marked the input nodes with red, hidden nodes with blue, prediction nodes with yellow, right? And also you can see an input layer, right? So you can see this as the input layer, this as the hidden layer, this as the output layer. The similar structure as we discussed in the previous slide, right? So next, what we are discussing is we are going to have some kind of inputs to the input layer. Let's say we have 2 as the input, right, for the first node. Then, apart from the nodes and the edges, there are something called weights, which is associated with the corresponding edges to the nodes, right? Then what it does is it multiplies the input value with its corresponding weights to this edge, right? So we have 2 as the input, we have 2 as the weight, and we are going to multiply them. Then we come up with an answer as 4 for the prediction in this hidden layer. The first node of this hidden layer comes up with the prediction as 4 for the input 2, right? So then what happens is, again we have another node in the input layer. So it has 3 as a value in this example. And also it has associated weight value 2. Then as we did in the previous example, we are going to multiply those 2 values together and we come up with 4 plus 6. So we get the final answer for the first node of the hidden layer as 10, right? So again, we have to calculate the values for the second hidden layer, the second node of the hidden layer, which is this, right? So in order to do that, we multiply this 2 with its associated weight value. So we need to find out the weight value now. So it's 1. So we are going to multiply those 2 values together and come up with the answer. Then again, we have 3 as input and we have to find out the associated weight value. It's 2. Again, multiply them together and come up with an answer. It's 6. And add those 2 values together and come up with an answer or prediction for the second node of the hidden layer, right? So now we have come up with answers for all the nodes in the hidden layer. Then we are going to look at the associated weight value of this node, right? This first node of this hidden layer. Then we multiply those values together, 10 into 1. Then we come up with 10. Then again, we multiply 8 with its associated weight value, which is minus 0.5. We get the answer as 4. Then we 10 minus 4, we come up with the output value as 6. So this is what happens in simple terms. in a forward propagation algorithm. And this is how an artificial neural network comes up with a prediction, right? And we had inputs 2 and 3. We had the prediction 6. So this is the explanation in simple terms, right? So you can understand what happens with weights and the inputs and how it gets processed to calculate the intermediate predictions, right? So then the next step of the machine learning pipeline is the model compilation. So we define 2 steps under this model compilation. First, we have to define the loss function. It's a kind of actually measures the model's performance in prediction, right? And also, as we all can see, model is good if the loss is lower, right? If the loss value is lower, we can determine it's a good model, right? And we are going to discuss about an example of loss function in the upcoming slides. So it's mean squared error. We will be discussing how it works inside the algorithm of mean squared error. And if you really want to look at some more other loss functions, you can visit to this site, the Keras API, and there are a lot of other loss functions out there you can use for different purposes. So you can visit this slide for more loss functions. So then the next thing we have to define under the model compilation is the optimization function, right? So in each training epoch, it updates the weights, right? In which way? It has to update the weights in a way that the loss is minimum, right? So as an example, we can take the stochastic gradient descent as an optimization function that we can use in the model compilation, right? And also, if you want to refer to more other optimization functions, you can visit this Keras API and look for some other optimization functions as well, right? So you can use them accordingly as per to the requirements. So now, in this slide, what you can see is we are going to talk about how that this loss value of an artificial neural network gets calculated inside, right? So we have discussed about the mean squared error loss function in the previous slide, and we have already discussed in order to compile and model, we have to define the loss function in it, right? So this is how, if we have an artificial neural network, this is how the loss value is getting calculated, right? So there are different algorithms, different loss functions. So based on the loss function that you use, it will calculate the loss value accordingly, right? So in this slide, what we are discussing is how the loss value of an ANN gets calculated if we use the mean squared error loss function, right? So as you can see a simple structure of a neural network. You can see some layers, right? This is the input layer, this is the hidden layer, this is the output layer. And you can see it's a kind of directed graph, right? You can see the nodes and edges, right? And also you can see these are the normal data points which we get the inputs. And also you can understand these are the points where we have to predict the outputs, right? According to the inputs we get from these input nodes, right? So as the first step, let's say we had an input of 2 and the associated weight value of that edge is 2. So then again other input value is 3, associated weight value is 2. Then as we did in the previous slide in the forward propagation algorithm, what it does is it multiplies these values together and add them. So 2 into 2, 4, 3 into 2, 6, 6 plus 4, 10. So the prediction for the first node of this hidden layer is 10. But let's say the actual value that we need to get for this node is 20. Right? So it's 20. So prediction is 10, actual is 20. So what's the error? It's minus 1. So since we are discussing about the mean squared error loss function, we have to calculate the squared error for that node prediction, right? So next, again, we are going to calculate the prediction for the second node of the hidden layer. So we are going to multiply 2 into 1, which is the associated weight value, 3 into 2, 6. So we have 8 as the prediction for the second node of the hidden layer, right? So we get the prediction as 8. And let's say the actual value that we need to get for this node is 3. So the prediction is 8, actually is 3. So what's the error? It's 5. And we calculate the squared error. Again, we are calculating the prediction value for this output node. So we have to deal with these hidden layer values and their associated weights, right? So 10 into 1, 10. 8 into minus 0.5, 4, 10 minus 4, 6. So the prediction is 6. Let's say actually is 1. So the error is 5. Squared error is 25. So total squared error 150. Mean squared error 150 divided by 3, 50. So this is the explanation of how the loss value get calculated inside an artificial neural network in simple terms, right? So the second thing that we need to specify when we compile and model is the optimization function. So in the previous slides, we have introduced you an optimization function, which is stochastic gradient descent, right? So in this algorithm, what happens is you can actually see you can look at this graph, right? So you can see this graph. So you can see how the loss value gets deviated along with the parameter values, right? So you can see when the loss value gets changed during this, along with these graph values, it comes to a minimum, right? So in this stochastic gradient descent algorithm, what it does is it start at a random point like this, right? Then what it does is until you're somewhere flat like this, where the loss is minimum, it finds the slope and take a step down, right? Then it stops at this place where the loss value is minimum, right? Until that, what it does is it updates the weights of the neural network, right? Until it get the minimum loss value. So that's how the stochastic gradient descent algorithm works inside an artificial intelligence neural network to optimize the weights of a model. So after compiling the model, what we have to do is we have to train the model, right? So normally when we are training the model, we need a data set, right? So the convention is we have to allocate 80% of the original data for the training data set, right? So in the training data set, we have 80% of the original data set and we have features and also the labels, right? If we are using the supervised learning algorithm, right? And also in the training phase, we use different batch sizes with different number of samples, right? And we train this model for number of epochs as well, right? So as inputs that we give to the model in the training phase is we input all the features, we input all the labels, and also we define how many number of epochs has to be gone through for the entire data set, right? So after training the model, what we do is we can actually evaluate that model. So this for this evaluation purpose, when we are preparing the data set, as we said, we allocate 80% of the original data to the training data set. We allocate 20% of the original data for the testing data set, right? So we use that 20% of the data for the evaluation of the model, right? Then after evaluating the model, we can get some kind of idea of how this model performs for the unseen data, right? The data which it has not seen, right? And also after evaluating the model, you can actually use that model if the model has come up with a reasonable accuracy, you can actually use that model to predict for the real-time data, right? And also, as we have discussed, in machine learning, we have two learning algorithms, which is supervised and unsupervised learning. We can train a model by using any of these algorithms. So there is another question. When we are training a model actually, right? So in deep learning or in machine learning, what we are dealing with is like we are dealing with a very large amount of data, right? So since we are dealing with very large amount of data, there's a problem when it comes to the training the model, right? It takes a lot of time, right? The training phases always take a lot of time when training a neural network, right? So what happens if the system goes down during this training? So it will lose lots of work that have been already done, right? So it's a problem. So what we are doing here is like we use a mechanism to put checkpoints on the model's weights during what? During the training phase, right? Based on the monitored loss quantity, right? So if we are going to save the model's weight, if and only if the loss has been decreased compared to the last training epoch, right? If the loss has been reduced, we are going to save the status of the model to an external file during the training. So what happens if there is an system failure? We have the most accurate weights with us, right? With the minimum loss, right? Minimum loss that we have achieved so far. So there's no risk. We can resume the model from there onwards after the system crash, right? So if you are not familiar with the term that I have used, this epoch, it's actually in a single epoch, the iteration, the training phase goes through the entire data set, and also one epoch consists of like many iterations, and one iteration is equals to like number of samples and number of samples divided by the batch size, right, which contains a subset of examples. So here I'm going to describe how that checkpointed best weights algorithm works when the training phase is happening, right? So we are going to describe what happens when that checkpointed best weight algorithm works. So as you can see, we are going to consider 5 epochs, in this example, right? So before training a model, you can actually understand the loss value is infinity, right? So it has not been improved because we haven't trained the model. So after the IPO 1, you can see here the loss value is 0.00025. So it has been improved. Or the loss value has been improved from infinity to this value after the first IPO. So as we discussed in the previous slide, so there's an improvement. Loss has been decreased. So what we have to do, we have to save the model state to external file, right? So in second IPO, we have this loss value, right? So as you can see, there's an improvement with the last IPO, right? So what we do, since there's an improvement, we are saving the model to external file. So in third IPO, you can't see any improvement. The loss value is same when you compare it with the last IPO. So are we going to save the model state to external file? No, right? Since there's no improvement. So in the IPO 4 also, we can't see any improvement. We are not writing anything to the external file. So in IPO 4, we have this loss value. We can see an improvement, right? We can see an improvement. So what we do is, we are saving the state of the model to an external file. So in case there's a system failure in between these IPOs, what happens? We already have the best weighted model with us, gets saved in the external file. So we can use that file to restore the model at the place where it has been left off, right? So next. So since we have discussed how the checkpointed wait method get executed, we are also interested to know what kind of details get saved when we are saving the best weights, right? So these are the information it saves to the file. It saves the architecture of the model, the details of the layer, how many number of nodes, what are the activation functions, and that kind of architecture details are getting stored. And also the weights of the model, and also the training configurations, and also the state of the optimizer, right? So this kind of details get saved to the external file. So apart from the things that we have discussed so far, actually we have discussed the basic construct that we use in machine learning and deep learning and artificial intelligence, right? So apart from the basic concepts, you have these machine learning concepts also, and also some other things as well, right? So I'm going to introduce these techniques to you so that you can actually refer to these things and look at to these things and come up with some intelligent systems, come up with some more intelligent systems, right? So one technology or one technique in machine learning is, like as we discussed, the fully connected neural network, right? So we discussed almost everything regarding this technique, right? So far. But apart from that, we have a machine learning technique called convolutional neural network, right? This network at least have a one convolutional layer, right? And also it has a kind of combination of convolution layers, pooling layers, and dense layers. So in RNN, the recurrent networks, the specialty is you have internal memory, right? Apart from the feed-forward algorithm that you use to predict something, it has an internal memory, right? So you can use that memory to process all the sequences of inputs, and you can see what kind of applications that we use this RNN, right? And in LSTM, it actually a development of this RNN, right? So it actually has the same kind of applications like RNN, but it has the way more the better performance than RNN, right? And also there's another technique in machine learning which is very much interesting. It's generative adversarial network, right? So here you have two models, right? So these models get trained simultaneously, right? So one model is the generator. So it learns to create images that look real, right? So there's another model, it's the discriminator. So it learns to tell real images apart from the fakes. So we have two models. So during the training, generator is progressively become better at creating images that look real, right? And also discriminator becomes better at telling them apart, right? So this process at one point reaches where discriminator can no longer distinguish the real images from the fake images, right? So this is what happens in generative adversarial network. So if you are interested, you can actually further refer to this machine learning techniques and try to come up with solutions. I just wanted to introduce these techniques to you because I need for you to go through more details about these techniques and implement or come up with some more products, intelligent products, right? So next, so far we have discussed about the theoretical stuff in artificial intelligence or machine learning, right? So now we are going to actually implement kind of a system, right, in Google Collaboratory, right? So if you want to use the Google Collaboratory, you can use this link and go to the site, and there you can find Jupyter Notebook environment. And the advantage of this is you don't require any setup, right? So it runs entirely in the cloud. And also you can use the cloud's resources to run your program as well. You can use their GPUs and other resources to execute your programs, right? So before using a Google Collaboratory IPython notebook, you have to set some configurations like this. I will show you how to set those configurations. So as you can see, you have to connect it to a, first of all, connected to a runtime. It can be the hosted runtime in the cloud, or else it can be the local runtime in your system, right? So in the examples that we used in this webinar, I'm going to use the hosted runtime because I'm using the GPU. Then you have to change the notebook's runtime settings to this. Select the runtime type to Python 3, and you can use GPU as the hardware accelerator. And if you want to run all the notebook code cells, you can select runtime and run all, right? And as the first practical that we are going to do is, as we mentioned in the today's outline, we are going to discuss how to implement a neural network which can actually do a multi-class classification, right? So in this example, we are going to train a neural network by using a fashion MNIST dataset, right? This MNIST dataset consists of fashion images. So we are going to train this neural network using some fashion data, and we are going to enable that model to predict or identify or classify the clothing images, right? So we will go through the IPython notebook, which is in the Google Collaboratory, and we will see how we can implement an intelligent system to identify or classify a multi-class problem, classification problem. So I'm going to shift to the IPython notebook solution. So as you can see, we are going to go through this solution. So first you have to, this is actually the IPython notebook that you have. Then before we are going to actually implement the solution, you can select the runtime, change the runtime type. If you want, you can use the GPU, which is hosted in the runtime. And also when you connect to this notebook, you can select the runtime, whether it's the hosted runtime or the local runtime, right? So after selecting those informations, you can actually write the code inside these cells and run the program and see the output itself, right? So in here, as the first step, what it has does is, it has imported the main libraries, TensorFlow, Keras, NumPy, Matplotlib, and some other libraries. So Matplotlib is there to print or plot the images. Right? And also this guide, in this guide, we actually train a neural network to classify images of clothing like sneakers and shirts. Right? So in this example, the dataset that we are using is the fashion nameless dataset. So this dataset contains 70,000 grayscale images in 10 categories, right? So the resolution of those images is 28 by 28 pixels. So as you can see, we have imported all the libraries. Here you can see we are loading the dataset, the fashion nameless dataset. So you can see here the dataset gets downloaded, right? And then you can see after downloading the dataset, you get 4 separate datasets, right? You get the train images dataset, you get train labels dataset, you get test images dataset, you get test labels dataset, right? So we get 4 datasets after loading this fashion nameless data, right? So after loading this data, you can actually explore the dataset. So first, we can explore the train images dataset and its dimensions. So when you execute this code, you get this as the output. As per to this, you have 60,000 images, which is 28 by 28 pixels resolution, right? So we have 60,000 images in the train images dataset, and also we have associated train labels, right? Which is of integers, right? So if you can see, so there are some labels for each and every this class name, right? So we have 0 as the label for the t-shirt. We have 1 for trouser, 2 for pullover. So we continue like that, right? So we have features and we have labels. And also we can explore the data sets that we have got after the loading the data set, right? You can explore the test images, you can explore the train images. So as you can see, we have 60,000 records in the training set and 10,000 records in the testing data set. So then you can actually, if you want, you can select one of the images that were there in the data set and plot to see whether the actual image is there, right? And then what we do is, we have to actually scale the pixel values of the images, right? Before we train the model, right? So before we train the values to the neural network, we are going to scale all the pixel values of the images into the range of 0 to 1, right? To do so, we are going to divide this pixel values of these train images and pixel values of these test images by 255, right? So we are going to scale. And after scaling, we are plotting all the images in the data set. We actually here we have plot 25 images and see whether it's correctly loaded, right? So we can see all the images with its associated labels. Then, as we discussed in the machine learning pipeline, what we have to do is we have to build the model. So we have to design the model. So here you can see we have developed a sequential model with 3 layers. So we have flattened layer as the first layer, dense layer as a second layer, and we have another dense layer as the third layer. Right? So we have 3 layers. Why we are having a flattened layer as the first layer? Because we are going to have a 2-dimensional input as the first input. Why it's 2-dimensional? Because an image is a 2-dimensional representation, right? So it's 28 by 28. So we first of all we have to flatten it into a 1D array. So we have 2D array as the input. We have to flatten that input to a 1D array. Why we are doing that is the dense layers can only accept 1D arrays, right? It can't accept any multi-dimensional inputs. So that's why we have used the flattened array as the first layer, right? And also we are using a dense layer as the last layer to give the predictions. And as you can see, we have defined 10 nodes here. Why? It's associated with the 10 classes that we had in the dataset. We have already defined the 10 classes here like this, right? So the output is going to be one of them. So we have, since we have 10 classes, we are going to define 10 nodes in the last layer. And the next step is to compile the model, right? The next step is to compile the model. So as we discussed in the machine learning pipeline, what we have to specify in the compilation step is, one is we have to specify the optimization function. Then we have to specify the loss function. Then we have to specify some kind of metrics to look at the evolution of this model, right? It can be the accuracy, it can be the loss, right? So in this case, we have used Adam as the optimization function, and we have used sparse categorical cross entropy as the loss function. Why we have used this loss function is, like in multi-class classification problems, sparse categorical cross entropy algorithm works far more better than the others, right? So that's why we have used this. So after compiling the model, what we have to do is we are going to train the model. So in Python, we have this fit method to train a model. So to train a model, what are the parameters we pass? We have to pass the train images dataset, which has a set of images, and then we have to pass labels, which contains the class name, right? So as you can, if you can remember, this is a kind of supervised learning methodology. We are passing all the training data and we are passing the labels associated with them, right? So after training the model, we can evaluate the model. To evaluate the model, what we have to do is we have to pass some data which the model has not seen, right? So all the data in the training data set has seen by the model, right, in the training phase. But if you can remember, we have allocated 20% of the original data set as the test data set. So we can use that data set to evaluate the model, right? So here we have evaluate method in Python to evaluate a neural network model. Then we have to pass the test images and test labels to it, right? Then we get the test loss and the test accuracy values, right? So as per this example, its accuracy after this training is 87%, around 87%, right? So you can see actually what the content that we are going through is the machine learning pipeline that we have discussed earlier, right? So if you can understand the machine learning pipeline, you can actually apply that to different scenarios, different problems to solve something in an intelligent way, right? So same pipeline gets applied to different kind of scenarios. The only thing gets different is the hyperparameters and some other fine-tuning parameters which we have to set as per to the requirements, right? But if you know the machine learning pipeline, you can apply that to many other different scenarios. So here, after evaluating the model, we can use this model to predict something, right? So we have trained this model with fashion data and its associated classes, right? So after training this model, what we are going to do is we are going to use this model to predict something. So for this purpose as well, we can use the test data set that we have allocated for the evaluation purposes, right? Or else we can use some other data, some completely external data to test this model which is compatible with the structure of the data that we have trained the model, right? Then after calling this predict method, which is given in the Python on the test images dataset with the set of images, we get set of predictions, right? It's an array, right? So we get predictions for all the images that we have passed to predict. Then here what we are doing is we are going to examine one prediction for one image. So we access the first element of this prediction array and see what are the things that it gives. So as you can see array, right? For the first image, as the prediction for the first image, you get an array, right? So these are the probabilities of the confidence of each and every class that we have mentioned earlier, right? So in order to find out the predicted class, we have to find the maximum probability. So that's the model's prediction, right? That's the class that model has predicted. So in order to find out the model, find out the class with highest probability that the model has come up with, you have to find out the maximum value, right? Maximum probability out of these values. That's why we are using this argmax method to find out the maximum value inside this array. Right. So as per to the output, you can see the maximum value is 9. Right? That means the prediction is 9. 9 means what's the class that is associated with 9? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ankle boot. Ankle boot is the associated value, associated class for the value 9. So the model has predicted ankle boot for the image, the first image in this test image dataset. Right? Then to verify that output that the model has given, we can actually test the actual value or the actual label of the first image of the test images dataset. So we are testing that here, right? So you can see it's also 9. So the prediction is right. The model has predicted that image as it is. It's an ankle boot, right? So we can verify. So here we have verified, we have plotted that image and verified that it's an ankle boot, right? So we can see the image and its prediction or the probability confidence. So the class 9 has the highest probability. So as you can see, we have plotted all the probabilities, prediction probabilities along with the test images. So after training and testing this model, right? So in the previous lines of code, what we have did is we have tested the model for set of images, right? But in actual cases, what we need to do is after training this model, if we pass some kind of image to this model, it should be able to predict it accurately. So in order to do that, we have to configure this model to accept one image, right? But if you can remember, when we train the model, we actually train that model in with badges, right? So the dimension of the training phase is not similar to the dimension of a single image, right? So when we train a model with badges, it's a three-dimensional input that we get, right? So when we are trying to insert an image which is of two-dimensional to a model that has been trained to get three-dimensional input, it's not possible, right? So in order to make this model accept a single image, we have to expand the dimension of this image by one dimension because the model accepts three dimensions, right? So that's what we are doing here. So we expand the dimension of the image by one dimension. Now, after expanding the dimension, we have three-dimensional input. So now we can pass this image to the model's predict method, right? Then we can get the prediction for a single image. So as you can see all the probability values for all the classes here. Then we have to get the maximum value out of these probabilities and find out the class that it predicts, and we can find out the associated class value of it, right? So that's how we are dealing with multi-class classification problems, right? So what I need you to understand is, as the beginners, actually you don't need to understand or remember all of these codes, right? But what you have to do is, you have to understand the machine learning pipeline, right? And what it does, right? What are the steps of it, right? If you can understand that, you can apply that pipeline details into different scenarios, right? So as beginners, you can get that detail from this webinar, right? So then thereafter you can apply this knowledge to different kind of domains and implement different kind of intelligent systems. So we have discussed how to deal with a multi-class classification problem. So next, what we are going to do is we are going to go through another practical example, which we are going to describe binary classification problem, and where we classify the movie reviews negative or positive, right? So here, the same pipeline is going to be applied as we have discussed. Same machine learning pipeline gets applied, but it gets different according to the special domains, right? Like this. So in previous case, we have applied the machine learning pipeline to image classification. So here we are going to apply this machine learning pipeline to text classification problem, right? So I'll describe the steps. So first you download the relevant libraries. So we can see the download process. And then again, we are loading the IMDb dataset, which contains all the movie reviews. And we are splitting the data set into 60% to 40%, 60% for the training data set, 40% for the test data set. And here we are kind of exploring the data. So we can see all the movie reviews, first 10 movie reviews of the data set. And we can see all the reviews. And you can actually see zeros and ones. So the negative and positive feedbacks has been classified to or converted to 0 and 1 value. 0 is negative, plus is positive, right? So you can see the label values as 0 and 1, since this is a binary classification problem. You only have 2 classes. In previous case, you had multiple classes. So then you build the model. Here you build the model. So here you can see a special thing called embedding layer, right? So here what it does is, here actually this model uses a predefined, already predefined model, pre-trained model, right? Which is in the TensorFlow hub, right? So you can use that already trained model inside this model that we are going to build, right? So that's called transfer learning. We are using already trained model in another model, right? So you can use TensorFlow hub to use some pre-trained models if you want to use them, right? So in this embedded layer, you have like when you are trying to classify and movie review, you have text as input, right? But normally neural networks can't accept the text values. So you have to convert them into integer values. So that task is done by this embedded layer, right? So after converting those text values into the numbers, we can actually get those inputs to the dense layers that we have defined here, right? So you can see the hub layer, which is the embedded layer, which has been created from the already trained model, which we have got from the TensorFlow hub. Then we have defined 2 dense layers, and we have defined activation functions. And here you can see we have just 1 node in the last output node. In the previous case, we had 10, right? Because we had 10 classes. But in this case, we have 1 class. We just have to figure out whether it's a positive or negative movie review, right? So that's why we are having 1 dense layer. So when you are calling this summary method, you can actually see the summary of the model. You can see all the layers, input shapes, output shapes, and all that, right? Then, as we discussed in the machine learning pipeline, we have to specify the optimizer, loss function, and matrices for the compilation step. In here, there's a specialty. You have to look at this loss function. It's binary cross entropy. In the previous example that we have discussed, what's the loss function that we have used is it's sparse categorical cross entropy, right? But in this case, we are using this loss function because for binary classification problems, this is the function that gives you the best output, right? So next, after compiling the model, we train the model. To train the model, you have to pass the training data set and all the training data set, and you have to specify the number of epochs. And there's a special thing that we have defined, which we have not defined in the previous example, which is validation data, right? We only have discussed about the separation of original data set into 2 data sets, which is trained data set and test data set, right? So we allocate 80% of the original data set to the trained data set, and we allocate 20% of the test original data set to the test data set. But in here, you can see another concept called validation data. We have this data set to validate the model during the training, right? So you can define the validation proportion that you have to test, and so some portion from the training data set gets allocated for the testing during the training phase, right? So you can evaluate the model as the training goes on, right? So that's a special concept. So after training the model, you can evaluate the model like this. To do that, you have to ask some test data and get the results. So you can see this model's accuracy is around 85%. Okay. So as you can see, and I have to request from you is don't try to get overloaded with all these concepts, but try to understand the basic machine learning pipeline, right? For these two use cases, I have used the same machine learning pipeline, right? But sometimes I have used some different features, but the pipeline is same, right? So if you can understand that, that would be enough as a beginner for the time being, right? So you can develop on that knowledge to build up some other intelligent systems. And if we have time, let's quickly go through a kind of regression problem as well. So here we are going to look at some implementation, how we can come up with an intelligent solution to basic regression, right? So here what we are doing is not like the things we did in the first two examples, the first two practical examples. What we are going to do here is we are going to predict the fuel efficiency. As we have discussed in regression, what happens is we are dealing with some real values, right? Like decimal point values, like dollars and salaries and some other stuff, right? Then as the first step, you can see, as we did in the previous example, we have to import all the libraries relevant. Then we have to load the data set. Here we are going to download the auto MPG dataset. You can download it from the internet. The dataset is there, and you can see the column names and the structure of the dataset. And here we have evaluated the structure of the dataset. You can see all the columns and the data that we have. And then what we did is, as we mentioned in the already mentioned in the machine learning pipeline, we have to kind of pre-process the data that we got. So here we clean the data, right? So to do that, here you can see it's using is now method. It's we are going to remove all the null values from the dataset, and it's a kind of pre-processing that we are going to apply. And also if you want to feed the data into a neural network, you have to remove all the categorical values, right? So in this origin field of the data set, you have the categorical data like USA, Europe, and Japan. Right? You don't have numbers, right? As we discussed in the previous examples, we can't insert numbers to the neural network. So we have to, what we have to do? We have to convert that to numbers, right? So we do 1 or 10 coding, right? So since we are running out of time, yes, we did some data pre-processing, and we have to then split the data into the train and test data. And here we inspect the data and find out the correlations in between those fields. And here we see all the statistics of each and every field. And here you can see we split the features from the labels. Here the label or the value that we need to predict is the MPG value, miles per gallon. And we normalize the data, because if we don't normalize the data, the model will depend on the units that we have in the data set, right? So it won't be generalized into some numbers. So then, as per to the machine learning pipeline, we build the model. Then we train the model by using the fit algorithm.
Hi, Sarala. Sorry to interrupt. We have another 5 minutes more.
Okay. I'll quickly finish this and move into the Q&A. Yes. So after training the model, as you can see here, you can use the dataset to predict. Okay, since we are running out of time, we will move into the Q&A session. So I have questions in Zoom and Slido. Sasindu Madhushan asks, does training mean saving this data in machine and after analyze them and get info? No, it's not actually saving this data. You actually have to get the data set for a specific requirement, and you have to train the model, like feeding all the data with all the features and labels. If you follow the supervised learning algorithm, then the model will be able to identify the mapping in between these features and labels. Then it will be able to predict the output if we provide something as input, right? So in training, what happens is we let the model to understand the mapping in between the features and labels. We are not going to save the training data inside the model. Why nodes? Isuri Gunatilak ask why nodes in each layer is not connected among themselves, like the nodes in the input layer is not connected to the other nodes. Actually, in a neural network, you have different kind of layers. You have the input layer, you have the hidden layer, and you have the output layer. If it is a dense layer only, all the nodes get connected with each other, right? So for the other layers, it's not a mandatory task to get connected with each other, right? Only if it's a dense layer, all the nodes get connected with each other. Lasinta asked how to bring a multi-regression analysis and make a decision. We have already discussed how to use a single regression problem, and yes, in multi-regression also we are dealing with real numbers, and we train the model to deal with multiple features and predict the real numbers. Hasita asks what are the programming languages needs to master other than Python and branch of maths? What are good resources such as online? Yes, the languages that you need to, I think, go through is machine learning kind of stuff. Python has been optimized, like Python, R kind of languages has been optimized. You have like all the libraries there if you use R, Python, and other data related libraries, right? So if you can use them, you can actually easily get done your work. And what are the online resources you have to study about the machine learning and other stuff? I would like to recommend you the TensorFlow site if you want to like start off the things in machine learning, and if you want to understand the concepts of machine learning and the practical related stuff, I recommend the TensorFlow side. We actually have the examples that we have gone through in this webinar is also like all the examples you can find out in the TensorFlow site. Yes. Shara asked, why do we use pre-trained model? Because actually, as we have discussed, you can use the TensorFlow hub, which is provided in the TensorFlow, to use the pre-trained models in a new model that we we are trying to implement, because we don't have to reinvent the wheel, right? If the solution has been implemented for a particular problem and the model has been developed and it has been already trained, why do we need to develop the same model again for our problem as well, right? So we can use a pre-trained model to avoid reinventing the wheel, right?
Sarala, I think with the limited time frame, I don't think we can. I think there are a lot of questions coming up. Yes. So I think we need to wrap up the session. So if you can just share the screen of the question, I think that will be great.
The most important part of this session is like we have a very good news for you. We are going to give you a question. You can take this home and try this practical, and you can actually go to this Collab notebook, and you had to follow the steps given in this notebook and build a simple convolutional neural network to classify the CIFAR images. You can actually get the understanding of the structure of this data set. I have given the link in this Collab notebook, and you can send all the answers with the Collab notebook Python script to this email on no before 10 a.m. 1st of June. And you can also share the Collab notebook links with the access permission to us. We will email this question to all the participants. So you can come up with the answer to this question and send to us. We will randomly pick a winner and give you a prize. Okay. Thanks for joining. And thank you for SLASCON for organizing this kind of event. So over to you, Tushar.
Right. Thank you so much, Sarala. So like Sarala said, we will email this question to every one of you so that you can email it to this email address, and Simcentric will pick a winner and we'll get back to them individually. And thank you so much, Sarala, for sharing your knowledge on machine learning. I'm sure it was very useful for everyone. And thank you everyone for joining in. So as this is the end of the session 1 of the Digital IT BPM Week last day, we have another session coming up at 6:30. We have industry experts coming on board on making workforce ready post COVID-19, a panel discussion. So looking forward to see you all at 6:30, and thank you.